You know those TikTok hacks that seem scientific but totally fall apart when you try them? That's bad experimental design in action. And here's the kicker. Even real scientists mess this up. You can collect all the data in the world and still be stuck if your groups are uneven, your measures are messy, or your sample just isn't what you thought it was. That's why good science starts with good design. Without it, your results can look convincing but be totally wrong. So whether you're fact-checking a viral hack or planning your first real study, this episode is your cheat sheet for doing science that actually works. I'm Megan Puglia, this is Unhidden Curriculum, and today we're unhiding how to think and plan like a scientist. Let's get into it. Before you run any analyses or collect any data, you've got to start with the big picture. Every solid experiment starts with a clear and measurable question. So ask yourself, what do I really want to know? Maybe your question is, does mother's touch improve infant bonding? Now that certainly is an interesting question, but it's too broad and vague. I can't measure bonding directly. Instead, I need to translate this big idea into something measurable. Maybe by bonding, I mean mom's reported feelings of connection with her baby, or how baby's brain responds to mom's touch. In research, this step is called operationalization, and it's what translates abstract ideas into testable science. So with operationalization, I can rephrase my question to be specific and measurable. Does the amount of skin-to-skin contact experienced within 24 hours of birth influence functional connectivity between regions of the brain involved in emotional responsivity? That's a testable question because we can measure functional connectivity using fMRI. Once you have a testable question, the next step is forming a hypothesis. A hypothesis is an informed guess. It's based on what we already know, not a random shot in the dark. And as scientists, we actually define two hypotheses for each question. First is the null hypothesis. This is the assumption that nothing is happening. There will be no effect or difference in your data. So if my question is, does skin-to-skin contact help infant brain development? My null hypothesis might be, there will be no difference in brain connectivity between babies who receive more versus less skin-to-skin contact. Next, we define an alternative hypothesis, which is what you expect if something really is happening. So in our example, an alternative hypothesis might be, infants who experience more skin-to-skin contact will demonstrate greater connectivity between regions of the brain involved in emotional responsivity. We test the alternative against the null to make sure any effect we find is real, not just due to chance. To test our hypothesis, we need variables. Variables are the things we can measure or change. First, you have your independent variable. This is what you control. In our examples, the amount of skin-to-skin contact. The dependent variable is what you measure, like brain connectivity. Here's a little trick to help you remember which is which. For independent, think input. For dependent, think data. Controlled variables are next. These are everything else you try to keep the same, like who provides the skin-to-skin contact and how old the baby is when they receive the skin-to-skin contact. At higher levels of research, we also think about confounds, mediators, and moderators. A confound is something you didn't control that could explain your results. This is like health complications that occurred during birth, cultural norms that might impact whether mothers choose to engage in skin-to-skin contact, or what time of day the baby was born. A mediating variable explains how an effect happens. For example, maybe skin-to-skin contact improves functional connectivity because it increases blood flow to the brain. And a moderating variable changes the strength of the effect. Maybe skin-to-skin contact improves brain connectivity only in babies who are born prematurely, but not in those who are born full term. These extra variables are critical in real research because they help us move beyond does it work to why does it work and when does it work. Now that you've clarified your hypotheses and variables, the next step is to figure out how you'll answer your question. There are two main branches of study design. The first is correlational or observational research. Here you measure naturally occurring variables and see if they're related. In our skin-to-skin contact example, you can observe how often a mother provides her newborn with skin-to-skin contact within the first 24 hours of life. Here, you're not asking mom to change anything about her natural behavior. You're just watching to see what she does. Now, an important consideration with this type of design is that correlation does not imply causation. What I mean by this is that just because two things are related or correlated doesn't mean one caused the other. Ice cream sales and shark attacks rise in the summer, but one doesn't cause the other. The hot weather driving people to eat cold treats and swim in the ocean is the real factor. The other major type of research involves experimental manipulation, meaning you change a variable to see if it causes an effect on your dependent variable. For example, you could tell some moms to provide skin-to-skin contact to their baby for 1 hour and others for 3 hours. Now, there are important ethical and practical considerations that may make it impossible to perform true experimental design. For example, it would be unethical to ask a mother to not touch her baby at all during the first 24 hours of life. This would also be highly unpractical, as the baby will need to be touched and held for things like feeding and diaper changes. Most experiments compare outcomes across groups, because if you only test one group, you can't tell what's driving the change in your dependent variable. That's why we often use control groups. They give us a baseline. For example, if you wanted to know if touch improves brain connectivity, maybe you assign one group to get extra cuddles and one group to get extra story time. Otherwise, you can't tell if the effect comes from the touch itself or just the fact that the infant had extra attention at all. There are two common study structures here. In between subjects designs, different people get different conditions. For example, one group of infants will get 1 hour of skin-to-skin contact, and another group will get 3 hours. In within subject designs, also called repeated measures, the same people experience multiple conditions. For example, all babies will get 1 hour of skin-to-skin contact on one day and will get 3 hours on another day. Each approach has strengths and trade-offs. Within subject designs are powerful because each person can be their own baseline, but they can create order effects. Like if everyone always does the 1 hour task first, maybe increases in functional connectivity are just due to the fact that the baby is older after the 3 hour task. The fix? Counterbalancing. Some people do 1 hour of skin-to-skin contact first, and others do the 3 hours first. This way, things like development, practice, or fatigue don't influence or bias the results. Biases are hidden influences that creep into results. To reduce bias, we can use things like randomized assignment, in which people are assigned to different groups by chance. Random assignment helps protect against hidden factors, those confounding variables that might impact results. Another form of bias can emerge when the participant or experimenter expects a certain outcome. For example, if I know which infant is in the extra cuddles group, I might, without realizing it, smile more at that baby or linger longer during testing. That tiny change could influence the outcome. To protect against this form of bias, we use blinding, which is just a way of saying keeping certain information hidden till the end. In a single blind study, participants don't know which group they're in. In a double blind study, neither the participants nor the researcher knows until the end. Another key step in experimental design is deciding who we're studying. In human studies, that means things like age range, since development matters, medical conditions, and exclusion factors like medications, handedness, or what languages are spoken. In animal studies, it could mean species or even strain, because different strains can behave very differently. The important thing is you should always be able to explain why you chose that population. For example, maybe you're studying 6-month-old infants because they are in a sensitive period for language, or only people with ADHD because that's your target group. Now, we can't study everyone in our population, for example, everyone who has a diagnosis of ADHD. Instead, we take a sample, a smaller group meant to represent the larger population. How we pick that sample matters for generalizability, which is how much we can say about the population based on the smaller group we actually tested. So how big should that sample be? That's where statistical power comes in. Power is your ability to detect a real effect if it exists. Power depends on how big the effect is, how many participants you include, and how noisy your data are. Noise can come from things like random messiness, tired participants, measurement errors, or missing data. Think of it this way. Trying to detect an effect in a small, noisy study is like trying to hear a whisper in a crowded room. The more people you test or the less noise in your measures, the clearer the signal becomes. The more likely someone's going to hear the whisper. Now, science is never about absolute certainty. It's about weighing evidence, and that means we can make two kinds of mistakes. A type 1 error is a false positive. That's where we say an effect exists when it doesn't. For example, telling a man that he's pregnant. In a type 2 error, that's a false negative. That's where we miss a real effect. For example, telling a pregnant woman that she's not pregnant. Finally, it's not enough to ask whether an effect is real. We also need to ask, how big is it? That's called the effect size. This is where we distinguish statistical significance, is the result unlikely to be due to chance, from practical significance. Does it actually matter? For example, with a huge sample, you might find that a new keyboard makes people type 3 milliseconds faster. Statistically significant? Sure. Meaningful? Maybe not. But sometimes even tiny effects do matter. A vaccine that lowers infection risk by just 1% can prevent thousands of cases when applied to a whole population. That's why researchers think carefully about effect sizes when deciding on sample size and how to interpret their results. So far, we've been talking about testing a clear hypothesis, looking for a specific effect we expect. But science doesn't always start with a crystal clear prediction. Sometimes researchers are just exploring, looking for patterns, relationships, or clues that could guide future studies. That's called exploratory research. For example, you might measure maternal touch, mental health, household structure, and birth factors without predicting which one will relate to infant-brain connectivity. Exploratory research is like being a detective without a suspect. You're just looking for interesting clues. Confirmatory or hypothesis-driven research, on the other hand, is like presenting your evidence in court. You have a clear hypothesis and a plan for how to test it. Exploration is totally valid, but it's important to be honest about what you're doing. If you peek at results and then pretend you predicted them, that's called harking, hypothesizing after the results are known. It's like moving the goalposts mid-game. Another pitfall is p-hacking, trying lots of analyses or tweaks until something looks significant. Imagine throwing every topping on a cookie until one looks tasty, but ignoring the recipe you claimed to follow. One solution is pre-registration. That's writing down your plan, hypotheses, variables, and analyses before you collect any data. Pre-registration keeps you honest and helps others trust your findings. Even when moving from exploratory research to pilot testing, having a written plan helps prevent accidental bias. Once you have a clearer idea of what matters, it's time for a pilot study, a small practice version of your experiment. Pilots help you catch problems early before you commit to a full study. Do participants get bored, tired, confused? Are instructions unclear? Do technical glitches or dropouts threaten your data? Think of a pilot like a rehearsal before the big show. You want to catch mistakes before opening night. Pilots can also check whether your manipulation actually worked. These are called manipulation checks. For example, if you use a stressful task, you might measure heart rate to confirm that stress actually increased. They can also reveal floor or ceiling effects, where everyone scores so low or so high that your task can't detect meaningful differences. By combining exploratory research with careful piloting and pre-registration, you make sure your experiments are both well-planned and honest. You discover what's worth testing and stress test your design before diving into the full study. Once you know your study is workable, the next question is, are your measures solid and trustworthy? First, reliability. Does your measure give consistent results? If you test the same person twice in close succession, you should get roughly the same answer. Think of a bathroom scale that always reads the same weight or a thermometer that gives the same temperature. Next is validity. Does your measure actually capture what you think it does? A questionnaire might be meant to measure bonding, but actually captures mother stress. That's invalid. Or using a step counter to measure overall fitness. It only tells you steps, not endurance or strength. Good science needs both reliability and validity. At the study level, we also care about internal and external validity. Internal validity asks, are the changes really caused by your independent variable, or is something else sneaking in? It's like making sure your recipe actually produced the cake you intended. Maybe your students scored higher because of extra tutoring, not your new teaching method. External validity asks, will your results hold up in the real world? Lab-perfect cakes may not taste the same at home. A face recognition task with cropped, grayscaled images is controlled but unrealistic. Testing recognition on every face passing by on a busy street is realistic, but messy. This is the classic Goldilocks problem. Too much control is accurate, but may not generalize. Too little control is messy, but realistic. The goal is to find just the right balance, controlled enough to trust your results, realistic enough to matter in the real world. Finally, even the best designed pre-registered study isn't the end of the story. Science advances when results are replicated, when other researchers or you later can repeat the study and get the same result. Replication builds confidence and shows that a result wasn't just a fluke of one dataset or one group of participants. Transparency, sharing your methods, data, and decisions, makes replication possible and strengthens trust in science. Even if your design is clever and your measures are solid, you still have to run it through two final filters: ethics and feasibility. Ethics make sure your study protects participants. Are risks minimized? For example, asking mom not to touch her baby for the first day of life might sound scientifically interesting, but it's not ethical. Informed consent makes sure participants know what they're agreeing to before they start the experiment. Participant safety and respect always come first. Next is feasibility, which asks, can you actually pull it off with the time, money, and resources you have? Maybe your study requires 1,000 participants, but your lab can only recruit 50. Think dream versus reality check. Brilliant ideas fail if they can't be executed. Good design balances curiosity, respect, safety, and practicality. Otherwise, even the most elegant study is just a thought experiment. Experimental design isn't just something scientists do in labs. It's a way of thinking that helps you make sense of the world. So next time you see a headline like "Coffee Cures Alzheimer's," pause and ask, how big was the study? What was the control group? How was the outcome measured? Could there have been bias or confounds? Even in everyday life, experiment. Want to know if listening to music helps you focus? Change one thing at a time, keep the rest the same, and track the results. That's experimental thinking in action. Designing a good experiment isn't about perfection. It's about asking clear questions, defining variables carefully, planning comparisons, and thinking ahead to replication. A well-designed study is like a well-built microscope. It lets you see the truth clearly. A poorly designed study, no matter how fancy, is like peering through a cracked lens. The better your design, the more your results actually move knowledge forward. How you design your study in the first place will directly inform how you analyze your data. So next episode, we'll build on this to dive into the basics of statistics. Thanks for tuning into Unhidden Curriculum, a podcast for the curious. If this episode sparked ideas or a mini existential crisis in your study, be sure to subscribe so you don't miss a thing. Until next time, ask focused questions, build smarter experiments, and of course, stay curious.